All right, today I want to talk a little bit about sampling proportions, hypothesis testing for one proportion. And the idea is, the first thing we need to talk a little bit about is the sampling distribution. So I hope this isn't rattling too much, but I've got a bag here full of different colored beads. And if we look at the bag as the whole population, there's a certain percentage of them, or say this bright orange here, that some percentage of them is a bright orange, and whatever that percentage is, that would be the population proportion. And what we're looking at then is what happens if we take out random samples. Hopefully this isn't rattling too much. So if I take out a random sample of that, I'll get some proportion in this scoop, and if I take a different random sample, I'll get another proportion in that scoop. And if I take a different random sample, I'll get a slightly different proportion in those scoops. So those proportions, the sample proportions, are going to vary from sample to sample to sample. But the nice thing is we know what that sampling distribution is going to look like. So let's talk about that first. The sampling distribution for p hat, what we expect to see is, again, we're going to use p as the population proportion. And p hat as the sample proportion. So population proportion would be the whole bag. We have some percentage of them that are orange, and then the sample proportion is what we get in our sample. And that's going to vary a little bit depending upon the sample. And if our sampling size is large enough, what I expect to see is a distribution that I can essentially call a normal distribution, where the mean of that distribution, mu sub p hat, would be equal to p. It's the population proportion. So if 10% of the beads that we're looking at were that fluorescent orange, then I'd expect 10% of my sample to come up as fluorescent orange. And if I were to take lots of samples, I'd expect some variation to happen around that 10%. But they should cluster close to the 10%. Sometimes I'd maybe get 9%, sometimes 11%. Rarely I might get 1%, or maybe I might get 80% in some sort of weird sample up there. But that would be really unusual. I'd expect to have it a lot of times getting something close to that middle sort of thing. And of course, the other thing besides the shape and the mean, the center of that distribution, we also want to know what the standard deviation is. And the standard deviation turns out to be the square root of p times 1 minus p over n in there, if we're trying to find the standard deviation of the sampling distribution. Square root of p times 1 minus p all over n is a good approximation of the standard deviation in there. But I did say that this happens if the sample size is large enough. And so we need a big enough sample in there in order for this to work out. So in order to do inference, we have to have a couple of things. We need that n times p has to be greater than or equal to 10 in order to do this. And we need that n times 1 minus p needs to be greater than or equal to 10 as well in there. So that we want a sample big enough that we're going to get it. We expect to see at least 10 successes and 10 failures in there as part of the thing. And of course, we have to have a simple random sample, but we also want, so in our sample, we want to have at least 10 of the beads to be red or be orange. So in my sample, I'm looking at the sample size times the proportion. I want to get at least 10 of them that are orange, and then 10 of them that are not orange. So the 1 minus p is the probability that you don't get something orange. That's kind of the one big condition. You also have that you want an SRS of the population, that our data is selected from a simple random sample of the population. Those are kind of small. Let me see if I can make those bigger here so that they're a little bit easier for you to see in there. And there's actually a third condition. The third one is that you want your sample to be less than 10% of the whole population. That if your sample is getting too big, the sampling distribution, we can't do the normal approximation in that case in there. So we're just gonna look at doing a normal approximation here in this case. We're gonna see those things are in set. So here is a hypothesis test, and let's see kind of how this works out. So it says an airplane's public relation department says that the airline rarely loses its passengers' luggage. It further claims that those locations where luggage is lost, 90% is recovered and delivered to its owner within 24 hours. A consumer group who surveyed a large number of air travelers found that only 103 out of 122 people who lost their luggage on that airline were reunited within the missing items within the next day. Is this evidence that the 90% figure is too high? And we're asked to use a 5% significance level. All right. Like other hypothesis tests we've done, we want to follow, there's a nice 4-step process to kind of do these things. The first thing we want to do is state our hypotheses. To say what is our null and our alternative hypotheses. So our null hypothesis, we're going to assume that the airline is correct, that the proportion is 90%, that 90% of the values, luggage gets returned within 24 hours. And the alternative hypothesis, we're concerned that the 90% figure is too high, which means that the true proportion is actually less than 90% in that case. So if the true value is less than 90% would be our alternative hypothesis. The null hypothesis is always an equals to. The alternative hypothesis is a less than. Our sample proportion in this case would be the 103 divided by 122. 103 divided by 122, I believe, is about 0.844. So 84.4% of our sample is looking out there. And so then what we want to do is we're going to assume that the null hypothesis is true. And if the null hypothesis is true, our sampling distribution should be, well, let's check. Let's check our conditions here. 0.9 times 122 is what? 0.9 times 122 is 109.8. So I'm expecting 109 times out of our sample. If the 90% is true, that is definitely more than 10. And then I want 1 minus 0.9. Where's my erase option here? Let me fix that here. Eraser. There's the eraser. Whoops. Erase. There we are. I want that 1 minus 0.9 times 122 as well. So 0.1 times 122 is 12.2. So both those values are greater than 10, so I'm safe to use my sampling distribution, assume a normal sampling distribution in here. On those cases, I'm expecting to get at least 10 occurrences where the baggage was returned on time, and at least 10 times when it was not returned on time. So we're within our ideas there that we can do this normal approximation. And so what we're looking for then with our hypothesis test is now what's the probability that I can get a sample with a proportion of 84.4% or less if the mean is really 90%. That's really kind of what we're doing with our confidence interval, is we're trying to answer that question. We're going to calculate a z-score because we're working with the normal distribution, and it's p hat minus p divided by the square root of p times 1 minus p all over n there. Sorry, my handwriting's a little messy there, but it's our sample proportion. We're going to take the 103 divided by 122 minus our hypothesized proportion of 90% over the square root of 0.9 times 1 minus 0.9 divided by our sample size, 122, and that's all underneath the square root symbol there. And so if we crunch that into our calculator, our second step here is to find the test statistic, and that should be 103 divided by 122 minus 0.9, and that should be in a set of parentheses. Divide by the square root. The square root works as a nice grouping symbol for us on the bottom. We want to make sure, though, that everything underneath ends up underneath the square root, so I'm there. And I'm getting a z-score of negative 2.05. So that means that my sample is about 2 standard deviations below the mean. It's fairly unusual to get something that far away from the mean. So I've got my hypotheses. I've got my test statistic as step 2. Step 3 is to find the p-value. And I'm either going to use table A or my calculator with normal CDF. And I'm looking for that bottom tail there. So I want to go negative 999 up to negative 2.05 to find that value. Or I'm going to look on table A and look up negative 2.05. And it gets a value of 0.0202. 0.0202. So there's about a 2% chance that just by random, if the mean is really 90%, I've got about a 2% chance of getting my 84% in my sample, getting a sample that has 84% in them. And we were given a significance level. Were we given a significance level? Yep, a 5% significance level. And since this is less than 0.05, I can reject the null hypothesis. We'll reject HO. Our sample suggests, maybe I'll type this out here. And let me make the font nice and big here so we can read it. Reject HO. The sample suggests that the proportion of people receiving their luggage within 24 hours is less than 90%. Oops, I spelled receiving wrong. There we are. So that would be sort of the conclusion that we'd come into, the fourth step of our value. So it's unlikely that we'd get a sample that has 84.4% of them in it if the mean was really 90%. That's unlikely, so I'm going to reject the null hypothesis in there. And so that's basically how to do hypothesis for a t-test. It uses that same 4-step process we've talked about before. We want to state our hypotheses. We want to calculate our test statistic. We're using a little bit different value formula that we're doing here, but it's still a z-score because we can use a normal distribution. We find our p-value off the table. And the p-value, again, tells us the probability of us getting something like our sample or more extreme if the null hypothesis was true. And a small p-value is evidence that the null hypothesis is false. It's unlikely that we should get that sample if the mean is really 5%, or really 90%. And so we reject that and say that the sample is really less than the 90% claimed by the airline. Okay? And then our third step, last step there, is to make our statement in there. So there's how to carry out a hypothesis test for one proportion. It's pretty straightforward to the ones that we've done before, but it takes a little bit more work to get through that. All right. Thank you.